Today we are going to be doing lesson 10.6, and this is three-dimensional coordinate systems. So previously we have been learning about two-dimensional Cartesian coordinate systems, and they have looked like this right here. So we have an x-axis and a y-axis. Today we're going to add a third dimension. So in three-dimensional space, an object can be located by its latitude, longitude, and altitude. In mathematics, we can extend the coordinate system to include three axes. In this extension, the third axis, the z-axis, is perpendicular to the xy plane, the Cartesian plane, at the point that is the common origin of all three number line axes. So what that means is we can take our two-dimensional coordinate system and we can lay it down flat. So let's say we kick this guy over and we got a new coordinate system. So imagine this is flat on the table in front of you. And going straight up into the air is a new z-axis. So the upwards direction is typically considered positive. This direction is typically considered positive y, and this direction is typically considered positive x. We are going to talk about three-dimensional planes within this coordinate system. We're going to talk about lines and the direction of that line within this coordinate system. We're going to talk about spheres today. But first, we're going to talk about the actual coordinate points. Yeah, coordinate points. For two dimensions, Cartesian coordinates, we had an ordered pair that took the form of x, comma, y. And that gave us information of where it landed on the graph. In three dimensions, we have what's called an ordered triple. And that's going to look like an x coordinate, a y coordinate, and a z coordinate. So our first example, example 1, we're going to plot these. So example 1. This is on page 473. I would encourage you to get your textbook out and follow along, because in a minute we're going to get to some more complicated topics, and it might be helpful for you to have pictures in front of you, because as you're going to find out, it's hard to draw three-dimensional things. I'm not going to do the best job. As a side note, in your answers in the homework, if you get something close, if I can at least tell that you know what you're doing, I'm going to say it's right. Please do your best to make it legible, but it's really hard to draw in 3 dimensions on a 2-dimensional plane. So let's continue with example 1. We have 2 points. For A, we have the point 4, 5, and 3. And for B, we have the point 5, -6, and -3. Let's start with A. We are going to take this, it's a 4, maybe that helped. We're going to take the 4x and we're going to go ahead and mark it. We're just going to find it on the x-axis first. So let's count 4 notches in the positive x direction. That's right there. Now let's count 5 notches in the positive y direction. Let's go this way by 5 in the positive y. 5. And now we need to go up 3 in the positive z-axis. So we're going to count up by 3 here. Now, this is kind of the tricky part, actually putting the point on the graph. So at first, let's just imagine, let's ignore we even have a z-axis, and let's do it as if this were just an x and y-axis. It is slanted, so be careful of that. We are going to draw a point away from the x-axis that is parallel to the y-axis, and it's going to create a rectangle. So I'm going to go this way, parallel to the x. I'm going to come this way, parallel to the y. This way is parallel to the x. And we're going to find our xy point. And now to find the z point, we are going to go upwards, parallel to z. And there it is. This right here, now I recognize these two don't quite line up, but from a perspective point of view, this point is closer to us, and so it doesn't look like it's exactly on this vertical line, or that's a horizontal line, but it is in line with this point right here. And that's why it's kind of tricky to draw these things. Let's plot B as well while we're at it. This was A. Now B is going to be a positive 5x, so we're going to add one more notch right here. This time we have a negative 6y, so we're going to count 2, 3, 4, 5, 6 in this direction. Let's go ahead and make that box. We're going to move parallel to the y-axis and parallel to the x-axis until we find the convergence. And now we're going to move at negative 3 in the z direction. 1, 2, 3. My lines have overlapped a bit. Sorry if that's hard to tell. It's right there. And we're going to move down by that amount. 1, 2, 3. And this is our point B. That is how to find, that's how to plot a three-dimensional coordinate point. Next, we're going to talk about lines. This is page 474. A line is determined by exactly 2 points in any coordinate system. Because the slope concept of two-dimensional Cartesian system is a ratio of 2 numbers, there is no slope concept for a line in 3 dimensions. In Cartesian space, we give direction to a line using a direction vector. A direction vector of the form A, B, C. So I hope you're reading along with me. That is of the form A, B, C. Provides changes in x, y, and z respectively as we trace movement along the line from one point to another point. So based on the definition that we're given on page 474, that means that the line through the points, point 1, x1, y1, and z1, and the second point, x2, y2, z2, is going to have the direction vector form of x2 minus x1, y2 minus y1, and then z2 minus z1. Let's do an example to see that in action. Let's do example 2. So we want to find the direction vector for the line that passes through the 2 points 4, 5, 3, and 2, negative 3, -1. Now, we want to designate one of these as 0.1 and one of them as 0.2. It doesn't matter which, as long as you keep them straight. So it looks like our book calls this one 0.2 and this one 0.1. Okay, so we're going to take the x of 0.2 and subtract the x of 0.1. Now we're going to take the y of 0.2, -3, and we're going to subtract the y of, there shouldn't be a comma there. We're going to subtract the y of 0.1, which is 5. Now we're going to take the z of 0.2 and subtract the z of 0.1. So that is -1 minus 3. Now, we're going to do the subtraction within the commas, so that is going to give us a direction vector of -2, -8, and -4. So this would have turned out the same, mostly, if we had chosen this as 0.2 and this is 0.1. What would have happened if we did that? The math would have given us a +2, +8, and +4. These signs are opposite one another, but these are the same direction vectors. Now that we have learned how to form a direction vector, we're going to learn how to make an equation for a line. Now, I have some confusing building blocks to give you, but once we move on and actually use those building blocks, it's not going to be as complicated, trust me. Let's go ahead and erase example 2, and we can let's just get rid of all of it. So, the equation for a line in 3 dimensions is actually a sum determined by a fixed point on the line and any non-zero multiple of the chosen direction vector. Before we consider the definition of the vector form of a line, considering the following operations. That sounds like a lot. That sounds really complicated. Don't worry. We're just going to learn 2 things quickly first. So let's look at these 2 definitions, the bottom 2 definitions on page 474. The real number multiple of a vector is n times a, b, c. Remember, this is our direction vector. This is the real number multiple, and that is going to be equal to n times a, n times b, n times c. So when we multiply a direction vector by a real number multiple, we distribute that n to every term within the parentheses, where n is any real number. The sum of 2 vectors, and then another point that we're going to learn is that the sum of 2 vectors, like if we were to take a, b, c, and add it to d, e, f, that would look like a plus d. Now, we are adding the similar terms. So in these 2 ordered triplets, the a and the d are both x terms. So when we add these 2 triplets together, or triples, we can add the a and the d because they're both x terms. We make a comma. We can add the b and the e, and we can add the c and the f. Those are some definitions that we're going to use in a minute. The definition below that, where xyz represents a point on the line, the vector form of the line through point 1 and point 2 is going to be the equation x, y, z is equal to x1, y1, z1 plus n times a, comma, b, comma, c. We just use the two things that we learned here and combine them into the new equation for a line. So that's probably super complicated, and it's okay if you don't understand every bit of that immediately. We're going to actually use it, and hopefully that will clear things up. So before we go on to example 3, let's quickly talk about a form that's going to help us out later. So this form is vector, the vector form of the line. It can be rewritten in the point form of a line. So what that means is we just add these two terms together. So we would distribute the n to the a, b, and c term like above, then we can add the terms just like here, and that would give us comma. I wonder if I should type it instead. That way it's a little bit more legible. So adding the two together, that's going to give us x1 plus n times a, comma. Now we're going to have y1 plus n times b, comma, and z1 plus n times c. Now let's use it. If you're not too lost. Let's do example 3. Okay, so we want to find the equation. Using it is so much easier than reading it, believe me. Find the equation, example 3, for the line containing the points 4, 5, and 3, and 2, -3, and 1. Now, these might look familiar to you from the previous example when we were finding direction vector. So let's save you some time. We already found out that the direction vector of these 2 points, so the direction vector, oh my gosh, I can type fine until people are watching. The direction vector of these 2 points, if you remember, was 2, 8, and 4. This can be reduced to 1, 4, and 2. And in this example, we've gone ahead and done that. So that means to form the equation for the line between these 2 points, x, y, and z, is going to equal one of the points, right? x1, y1, and z1. We can choose either one of them. It doesn't matter. Let's say this is point 1, this is point 2. We're going to choose point 1, and we're going to plug in. So point 1 is 4, 5, and 3. And we're going to add to it this real number multiple n multiplied by the direction vector 1, 4, 2. So we're just plugging things in. We're taking pieces and we're putting it in a big equation. So this real number multiple is always n. It's always symbolized as n. The direction vector we've already found over here. We just plugged it straight into this point right here. And then either of these points would have given us the same equation of the line. Just like we could find the distance between two Cartesian points, we can also find the distance between two ordered triples. The equation is very similar. I have it written for you up here. This is on page 475, theorem 10.6.1. We're going to use it to find the distance between two three-dimensional points. So let's do example 4 together. In example 4, we want to find the distance between point 1. Let's go ahead and designate it as we write it out. Point 1 is going to be 5, -7, and 2. And then point 2 will be 2, 5, and 6. So we've designated point 1 and point 2. That makes this x1, y1, and z1. And down here we have x2, y2, and z2. We're going to plug all that into our equation. So d is going to equal the square root of x2, that's 2, minus x1, 5 squared, plus y2, minus a -7, that gives us plus 7 y1 squared, plus z2, 6, minus 2 squared. Now, this looks very similar to Pythagorean's theorem because that's what it's derived from. And we can do this math really quick. So 2 minus 5, let's see, 2 minus 5 is -3 squared. 5 plus 7 is 12 squared. And then 6 minus 2 is 4 squared. All of that under the radical sign. -3 squared, don't forget your parenthesis. Don't forget that the negative sign is also being squared. That's going to give us square root of +9 plus 144 plus 16. Adding all that together, that's going to give us the square root of 169. 169 is a perfect square, and that is 13. So the distance between these 2 points, point 1 and point 2, is 13 units. We can also take what we know about finding midpoints and apply it to 3 dimensions as well. So you might remember the midpoint formula it's actually given to you on page 476 for 2 dimensions was x1 plus x2 over 2, comma, y1 plus y2 over 2. And this looks very similar to an averaging equation because it is. For the midpoint of a 3-dimensional system, we are just going to add in the 3rd dimension. And by add, I mean put it in. We're not doing addition. to it. And we're going to do another comma and have z1 plus z2 over 2. This is how to find the midpoint of a three-dimensional line. And we're going to go ahead and do that in example 5. Okay, so we want to find the midpoint M of the points P1, that is 5, -7, and 2, and P2, which is 2, 5, and 6. So let's do it. Let's plug it all in. This is x1, y1, and z1. Down here we have x2, y2, and z2. That means that our capital M midpoint is going to be x1 of 5 plus x2 of 2 over 2, comma, y1 of -7 plus y2 of 5 over 2, and then z1 of 2 plus z2 of 6, and that is over 2 as well. If we are to do the math on all of that, this is going to simplify down into 5 plus 2 is 7 divided by 2, that is 3.5. -7 plus 5 is -2 divided by 2, that gives us -1. And then 2 plus 6 is 8 divided by 2, that gives us 4. So the midpoint of points 1 and point 2 is x is 3.5, y equals -1, and z equals 4. Now we're going to talk about planes. In space, a plane is determined by 3 non-collinear points, 2 intersecting lines, or 2 parallel lines. What that means, collinear would mean 3 dots that are in line with one another. These form a straight line. These are collinear points. Non-collinear points would simply be 3 points that are not in line with one another. And if you were to connect these points, you create a plane right here. There can be 3 non-collinear points. It can be 2 lines that intersect, and that creates a plane. It can also be 2 parallel lines that create a plane in between them. In space, we first consider planes that are determined by 2 intersecting axes. The xy plane is determined by the intersection of the x-axis and y-axis. By the intersection of the x and y axes, rather, has the equation z equals 0. Determined by 2 intersecting axes, there is an xy plane where y is equal to 0. I'm sorry, an xz plane where y is equal to 0, and a yz plane where x is equal to 0. What that means is in our xyz plane, in our xyz coordinate system, whenever z is equal to 0, right down here at 0, we have the x and y axes form a plane, the xy plane. Whenever y is equal to 0, the z and x axes form this plane right here. And then whenever x is equal to 0, the y and z axes form this plane. So, where a, b, and c are constants, The planes that are most easily described are those in the form x equals a, y equals b, or z equals c. So by that it means constants. For instance, z equals 2 is a plane that is parallel to and 2 units above the xy plane. So remember, the xy plane is this plane right here. And if we were to take the z-axis and go 1, 2 units above, the plane z equals 2 is this xy plane moved upwards by 2 units. I'm not going to draw that because that's kind of tough. It'd be kind of like that maybe, where this is the center now. I don't know. Well, I do know, it's just hard to write it. Likewise, x equals -4 is a plane that is parallel to the YZ plane. Okay, so YZ is this plane right here, but 4 units behind. So we would count 1, 2, 3, 4, and we would create a new plane back here where its center is x equals -4, and it's parallel to this ZY plane in front of it. There are numerous similarities in the two-dimensional and three-dimensional coordinate systems. However, the graph of the equation for the linear equation, ax plus by equals c in 2 dimensions is a line, while the graph of the linear equation ax plus by plus cz equals d is actually a plane. So previously we were working with ax plus by equals c, right? And this is our general equation of a line. We could turn this into y equals mx plus b using some algebra. This time, however, this is for a line. Whenever we add the third variable, we are now generating a plane, a flat plane, and that is going to have the general equation ax, so this is old, not using this anymore. Well, we certainly can in tests. It's still a relevant concept, but now we're on 3 dimensions where the general form of a plane is ax plus by, that's a b, plus c z is equal to a fourth constant d. It is still convenient to graph this plane by using intercepts. So remember, the y-intercept in Cartesian coordinates is when a line had an x equal of 0 and it crossed the y-axis. So for this right here, for this line, the y-intercept is y equals 2, because that's when x equals 0. We have the same terminology when we're plotting a plane. So the x-intercept, if we were to plot it, has the coordinates a, whatever value of x, with 0y and 0z, because we are touching the y and z axis and passing through, intercepting the x-axis. The y-intercept is going to have form 0x, some number y, and 0z. And then the z-intercept is going to have the form 0x, 0y, and some number c. Let's do example 6 to plot some intercepts and get more familiar with this concept. So example 6, this is on page 477, we want to sketch the graph of the equation x plus 2y plus 3z is equal to 12 in a three-dimensional coordinate system. So what are we going to do? Well, let's go ahead and draw our coordinate system. We're going to have a y-axis, an x-axis, and a z-axis. This is positive y, this is positive x, and this is positive z. If we want to find the x-axis, the x-intercept, we would simply plug in where y is equal to 0 and where z is equal to 0. So let's do that. Let's say that x plus 2 times 0, which is 0, plus 3 times 0, which is 0, is equal to 12. We see that a plane is going to intercept the x-axis at x equals 12. So let's go ahead and write that. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. This is where our plane is going to touch the x-axis. Now we can solve for the other intercepts. Let's solve for the y-intercept this time. We're going to have x equals 0 plus 2y plus another 3 times 0 is equal to 12. Dividing by 2, we get y by itself, and that's going to equal 6. So on the y-axis, we're going to count 1, 2, 3, 4, 5, 6. The plane is going to intercept the y-axis at this point. And now we're going to do the same for z. So x of 0, y of 0 is going to give us 3z is equal to 12. Dividing by 3, that's going to give us that z is equal to 4, which means we're going to count 1, 2, 3, 4. And these are the 3 non-collinear points of our plane. So we can connect these dots here, here, and here. And now we have drawn a three-dimensional object called a flat plane. And you can see a prettier picture of this in figure 10.47 on page 477. Now, we've covered a good bit of material. It can be a lot. Three-dimensional coordinates can be a lot to get your head around. So, if you would like, you can go ahead and pause this video and do homework problems evens through 22. The full homework assignment is more. The full homework assignment is through 33. However, if you need to pause, take a minute, unpack, cool down, practice what you've learned, we can move on to the rest of this lecture's content. So go ahead, if you'd like to do that, pause the video. If you're still watching, you don't feel that's necessary, or you have already come back, and we're going to continue with 10.6. We are now going to move on with relationships between lines. There are 4 possible relationships between 2 lines drawn in Cartesian space. First, 2 lines with different direction vectors. Now remember our general equation for a line L, that's a script L, is x, y, z plus in a constant times the direction vector a, b, c, where x, y, z is a point that the line contains. A, B, C is the direction vector. 2 lines with different direction vectors will intersect at a point x, y, z. In a point, if the x, y, z coordinates of the intersecting lines are respectively equal, When we do example 7, you'll see what that means, but intersecting lines are simply two lines that do not share a direction vector. They go in different directions, but they cross at a point x, y, z. The second possibility occurs when two lines, again, do not move in the same direction, but also never cross paths. Now, in 2 dimensions, whenever we had two lines that didn't go in the same direction, they always crossed paths. But now we have a 3rd dimension where, I'm going to try to draw it. It may not work out. So if we had a line like over here that was is going like this way, and it's in the positive x, positive y, positive z, and we had another line that went down this way in a different direction, but it's in the negative x back here, it's going to go behind this line, and they're never going to touch. Different directions that do not intersect at a point. These are called skew lines. So these intersect, these are skewed. There's a third possibility. Two lines that have the same direction vector, ABC, may be parallel, right? You know what parallel means. It just means they move side by side at a constant equal distance from each other. That occurs when the direction vector is the same. And then we have a fourth possibility, which is, what's it called? Coincident lines. So a coincident line has the same direction vector and the same point. What coincident means is, here's one line, the other line is exactly on top of it. Those are coincident lines. So let's draw that. Let's learn a little bit more about intersecting and skew lines in example 7. Just as a side note, coincident lines, this doesn't have to look exactly the same. The direction vectors can be the same without having the same numbers, and that matters. They can be the same because of this in term, right? Because if we had a direction vector of 1, 2, and 3, and an in term of 2, that's equal to a direction vector that has 2, 4, and 6. That's not supposed to be a negative sign. And a in term of 1. These are the same, right? If you multiply the in term through, you get 2, 4, and 6. Just that's a side note of coincident lines. Let's do example 7, where we're going to determine if two equations for a line are skew lines or if they intersect one another. And if they intersect, what is the point of intersection? So, if the lines intersect, then there are values of n and r for which a point on the line is identical. So, what we're going to do first is convert the two equations that were given. Let's draw them out. Take out that one. This is the general form. We're going to have line number 1 with the equation 1, 2, 3 plus n times direction vector 2, 5, negative 6. We're going to have a second line where the point is going to be 5, 7, negative 7. And it's going to have r multiplied by 1, 5, and negative 4. Now, we can tell these direction vectors are different. There is nothing we can multiply these two direction vectors by to make them equivalent. Therefore, they must either intersect or be skewed. So, if the lines intersect, then there are values of n and r for which a point on the line is identical. Let's convert these into, that's supposed to be a 2, let's convert them into point forms. So a point form is going to be combining these two additions. So what that means, we're going to have an L1, and now we're going to combine these x terms. We're going to multiply the n through and combine x terms. So that means the x is going to be added to n multiplied by a. Do you remember this? The y is going to be added to the n multiplied by b, and the z is going to be added to the n multiplied by c. This is the point form. I believe I talked about it earlier in this lecture. We're going to convert all these general equations of lines into the point form to make it easier to solve. So we're going to take 1 and we're going to add to it n multiplied by 2. Now we're going to have a comma. We're going to take 2 and we're going to add to it 5 multiplied by n. And now we're going to take 3 and add to it a negative 6 multiplied by n. We're going to do the same with the second line. This is going to give us this 5 added to r times 1. That's just going to be 5 plus r. And we're going to have our y term added to the 5 times r. That is this y term 7 added to this b term 5 times r. And we're going to have a comma. Now we're going to have the z term negative 7 added to a negative 4r. Now that we've done this, if there is a point of intersection for the two lines, then we're going to be able to set these two equal to each other, these two equal to each other, and these two equal to each other. That will be an intersection of these two lines if there are values of n and r that cause all of these equations to be equal. So let's do it. We're going to take these two and we're going to solve for n and r, right? Because we have two variables and two equations, that means we can solve for the two variables. Let's rearrange. Let's set these two equal to each other, right? So that's going to give us 1 plus 2n is equal to 5 plus r. Now if we were to solve for r would equal negative 4, right? Because we're going to subtract 5 plus 2n, because 2n is going to stay where it's at. Now let's go ahead and set these two equal to each other. This is actually going to be over here. So we're going to set 2 plus 5n equal to 7 plus 5r. Now we can solve for n in this equation if we plug in r from over here. So we're going to have that 2 plus 5n is equal to 7 plus 5 times the quantity negative 4 plus 2n. Now, solving for n, we see that 2 plus 5n is going to equal 7 minus 20, distributing this negative 4 into the 5, plus 2 times, plus 10 times n. Combining like terms, that's going to give us 15 is equal to 5n, which means that n is equal to 3. And if n is equal to 3, we can plug that back in over here and find that r is equal to 2. Now, if we plug n equals 3 and r equals 2 into these equations, point equations for lines, we can get 3 ordered triples. So we're going to do that. So let's do the first one first. If we take n and plug it in, 2 times 3 is going to be 6 plus 1. That's going to give us 7, right? 2 times 3 plus 1. Over here for the y coordinate, we're going to have 3 times 5 is 15 plus 2, that is 17. And now for this z coordinate, 3 times 6 is 18. Is 18. 3 minus 18 is negative 15. Now we'll do the same with r. I'm going to do it a bit faster this time. 5 plus 2 is 7. 2 times 5 is 10 plus 7 is 17. And then 2 times 4, negative 7 minus that term is negative 15. So we see that after solving for n and r, and after plugging those values of n and r into our original line equations, we get the same point. That means that line 1 and line 2 intersect at this point. They're equal to each other when x is 7, y is 17, and z is negative 15. Now, if we had done that equation and it turns out that our z values are different, they would be skew lines, right? Because they might be traveling in the same, they might cross through the same x and y point, but if one is like down here and the other is way up here, they don't intersect. They're skewed from one another. Same thing as if they had different y points or different x points. So in table 10.5, there is a summary of how you can look at the general form or at the equation for a line to determine whether they coincide, intersect, skew, or are parallel. Let's see. I am going to skip the intersection of planes section because it's really complicated. If you thought this was a lot, which it is, this is a lot of information to throw at you at once, then intersection of planes is a whole new level of that. So we're not going to do it. We are going to be skipping example 8 and example 9, which means we are going to end this lecture on example 10, talking about spheres. So this is on page 480. Previously we learned about circles and radius and pieces of circles and eventually spheres and volumes of spheres. Now we're going to learn about how it relates to a coordinate system and how to graph a sphere on a coordinate system. So in Cartesian space, the counterpart of the circle is the sphere. To find the equation for a sphere, we apply the distance formula, where the points, or where the point h, k, l is the center of the sphere with a radius of r. The points on the sphere, on the surface of the sphere, x, y, and z must lie at a distance r from the center. What that means is when we had a circle and we had points on the surface of the circle, each one of those points was an identical distance r away from the center. It's the same with a sphere. Let's try to draw a sphere. That's not so bad, actually. When a sphere has a center of h, k, and l, it will have a bunch, infinite actually, points of x, y, and z that are on the surface of the circle, and each of those x, y, and z points are an equal distance r away from the center. So this relationship leads us to the equation square root of x minus h squared plus y minus k squared plus z minus l squared is equal to r. So if we were to square both sides of the equation, we would be given theorem 10.6.3. You can find that in your book on page 480. The general form, you guys can read all the stuff attached to the theorems. I'm just going to go ahead and use it. So let's go to example 10. And we want to find equations for spheres. So let's do example 10. And problem number A is we want the center of a sphere, or we want the equation for a sphere whose center is at origin and the radius has a length of r. So our equations are going to be in x, y, and z format. We know that our r is equal to 5 and that our h, k, l is equal to 0, right? 0, 0, 0, because it's at origin. This makes our theorem 10.6.3 pretty easy. We can actually just go straight to our corollary, 10.6.4, that reads the equation for a sphere with the center 0, 0, 0 and radius length r is given by the equation x squared plus y squared plus z squared is equal to r squared. So that means our equation is going to be x squared plus y squared plus z squared is equal to our r squared. 5 squared is 25. So this is the equation for A. Now we could have done this the long way as well. If we had plugged 0 in for h and 0 in for k and l, we would have gotten x minus 0 squared plus y minus 0 squared plus z minus 0 squared. It would have given us the same thing. Now, let's do an example where we are not at 0 origin, or where our center is not at origin, rather. So this time, our radius is equal to 4, and our center, HKL, is at 2, -3, and 4. So we are going to plug those values into our equation. Plugging 2 in for h, that's going to give us that, it's going to give us x minus 2 squared added to y minus k. K is negative 3. Y minus negative 3 is y plus 3 squared. And then for the z term, z minus L, that's z minus 4 squared. That's going to equal the radius of 4 squared. And we can write that in a bit more of a simplified term by, we're going to go ahead and square that. So this is an answer that I would accept. They say that you could go ahead and expand this, where you would use the FOIL method to multiply these terms together. I'll take either. If you use the FOIL method, then you get the general form of the equation. That's just a lot of extra work, and honestly, this is a much more useful equation. So that is the end of 10.6, and it's a lot. I get it. It's hard to grasp. It can be hard to understand. If you guys need help with something, please ask. The homework for this week is going to be even numbered problems through 32. This will not include any of the content presented in examples 8 and 9. Good luck with the homework. I'm hopefully going to have Chapter 10 test made and given to you next week. And have a good week.